Hello all. Today we'll be looking at the course Advanced Data Structures and Algorithms. These are the CEOs for each of the module and for the overall syllabus. The assessment pattern is continuous internal evaluation will be 50 marks and end semester will be 50 marks of 2.5 hours. And we'll have these many internal assessments, either a series exam or a quiz or an open book text. Then project or an assignment, a course related task for 15 marks, and either a review paper, seminar, or any other type of another kind of assignment for 15 marks. The pattern for the exam is the same as S1 subjects. Okay, moving on to the module 1. We'll be looking at basically a complexity analysis method, that is amortized analysis, and some string matching algorithms. The second module deals with some kind of advanced data structures, the topics which you have not learned in the previous BTech data structures course. And the third module is dealing with properties of graph and algorithms that deals with graphs. Then the fourth and fifth module deals with mechanisms of solving algorithms like probabilistic algorithms and approximation algorithms, where we'll be looking at different algorithms for solving, like vertex cover, traveling salesman, etc. Okay, moving on to the first module. We'll look at the first, basically you need to have a revision of what is complexity analysis, times and space complexity analysis especially. So have a revision of that. And we have learned some asymptotic notations like big O, theta, omega, etc. So just have a revision of what are all those. And we look at another kind of complexity analysis known as amortized analysis. So basically, we can see here that amortized is basically to pay off a debt, usually by periodic payments. So it's a term that deals with the banking system where you pay off a loan or a debt by some installments or some regular periodic payments every month. So the term amortization comes from the banking sector. So here what we're going to do is we're going to look at some algorithm analysis methods, basically three of them that comes under amortized analysis, that is aggregate method, accounting method, and potential method. So an amortized analysis is basically some creative accounting for operations. What we are trying to do here is we can show that the average cost of an operation. So you know that what's a data structure, and every data structure is there's an operation associated with the data structure. So when you look at the complexity of these operations, it varies from data structure to data structure. So we'll be able to show that the various average cost of an operation is small when averaged over a sequence of operations and not on the dependent on the inputs. So maybe in some cases, maybe some data structures we have seen where the insertion operation is very expensive, means it takes more time complexity, but whereas maybe deletion is not at all expensive. So there are cases like that. So, but when we take a sequence of operations like multiple insertions, deletions, insertion, deletion, etc. So we can show that the average cost of an operation is small when you take at the expense of a sequence of operations and not just on what is the input size. So these results must hold true for any ordering of these operations. So unlike other algorithms where you may look at average case or something like that, this is not like that, and there is no probability also involved in it. So this is only an analysis method. There's nothing else to look into here. So there are three ways to determine an amortized cost of an operation that is part of a set of operations, we can say. So we don't look at a particular single operation, we look at the sequence of operations. So the time required to perform a sequence of data structure operations can be averaged over all the operations that are performed. So it can be so it is basically to show that the average cost will be smaller if we have a sequence of operations, even though maybe the single operation might be very costly, like I said before. So three methods are aggregate analysis, accounting method, and potential method. So basically, you can see the summary is given here. We find an upper bound for the total cost of sequence of n operations. For amortized cost, you can say it's basically the average cost per operation. That is, if T of n is the total, you can say that cost, then divided by n shows the average cost per operation. So there'll be the average cost per operation will be same over all the operations in the sequence. Like one of them will not have a high cost, another one will be less. It's not like that. They will have the same cost. The second one is the accounting method, where you can say that the cost can vary across operations. That is, you try to charge some of the operations, whereas you do not put any charge on other set of operations. So we'll look into that later. Then potential method is also like that, but in accounting method, we talk in terms of, you can say credit charging and all. But when it comes to potential method, we say we give some extra potential energy, we say in the form of energy, we discuss this method. We'll look all three of them in detail. So looking at the first one, that is aggregate analysis or aggregate method, you can say for all value of n, say n is a sequence of operations. Say you have a data structure D, just a second. Okay, you have a data structure D, which may have some sequence of operations. Say you have one insertion, another insertion, then maybe a deletion, then a third insertion, then another deletion, etc. You have a sequence of n operations. So we can say a sequence of n operations, the worst case time taken by it, yes, you can say it is T of n. Okay, the time taken for performing an operation on n operations. So in the worst case, the average cost or the amortized cost per operation can be denoted by Tn by n. And it will be the same for all the operations in the sequence. So in order to understand these examples, we'll look at traditional, no, not traditional, we look at a new kind of stack operation known as multi-pop. Okay, so before moving on to multi-pop, we should know what does traditional stack operation looks like. Like we all know what is a stack. Stack is basically a last in, first out. Is basically a last in, first out data structure where it is maybe implemented using an array, you can say. So any element that comes in moves to the end of the array like this, and the next element that is put will come on top of the previous element, and so on. And this way it grows upwards, you can say. If the opening is at one end, then it's the insertion as well as the deletion both takes place through that end. And the operations will be named as, you can say, push, pop, etc. Okay. So this push is something that pushes an object onto the stack, and pop is that whatever, if you have a pointer named as stop every time you insert an element. So using the stop pointer, you insert the element and as well as you delete the element. So once you insert an element, the top point was incremented and it is added there. So when it is deleted, you have to decrement the top pointer. That's all. So the element will be actually there in the memory, but eventually it will be deleted later. But the top pointer till 0 keeps track of all the elements. So from top till 0, these are the elements of your stack currently. So when you decrement the top pointer contains the topmost element of the stack. So that is what all about push and pop. Now, usually, what is the time taken if we usually try to perform analysis on this? We see that it just O of 1. It's a constant time because you just have to increment it, add the element. Adding element to an array does not take any much time. And similarly, you just have to decrement it by, so that in turn it will delete the element. So the actual cost of sequence for n push and pop is basically, you can say it is n itself. Okay. So if you have n push or pop operations, n times you have done the operation, right? So the total cost of the sequence will be n. Okay. So now we look at a new stack operation known as multi-pop. So we'll see what is multi-pop. Multi-pop takes into arguments, that is the name of the stack, as well as the, you can say, the element, how many times it has to be popped. Okay. So multi-pop, you can see here, it takes k elements from top of the stack. So if the stack is about to be empty, then you can say k elements cannot be popped, right? Only if the size of the stack contains at least k elements, you can pop k elements. But if it is lesser than k elements, then the entire stack will be popped. Okay, so say for example, I'm asking you to pop three elements, and the stack contains only two elements. So can we pop k elements? No. So because the size of the stack is 2 is already less than the required number of elements to be popped. Required number of elements was 3. Okay, but the stack contains lesser number of elements. So the entire thing has to be popped. But suppose it has many number of elements like this. We have a number of elements, and I'm asking you to pop any 3 elements. It will be the first 3 elements like this, and the remaining stack will be intact. Okay. So what is a multi-pop? It is nothing but inside a loop, you're repeatedly calling the pop function. All of you know what a pop function does. It just pops one element, and push is just pushing one element. So pop means deleting. So when I create a new algorithm like multi-pop, I just write like this. You have a loop while stack is not empty and k is not equal to 0. Okay, at least k has some value. It means a value greater than 1 or more than 1. And you do a pop on the element and then decrement the value of k. So initially, if you had, say, okay, so if you had a set of elements like this, and the k value, suppose it is equal to 3, and I have 4 elements in the stack, and I'm asking you to delete 3 elements. So 4 will be deleted, 2 will be deleted, and 3 will be deleted. So every time the loop has to work, we just decrement the value of k so that it works 3 times. So from 3 to 1. Okay. And till it becomes, if it is not a 0, then we keep on deleting using the pop function. So multi-pop, the actual cost for stack containing S items. If the stack has S number of items, then you can say the cost for one pop is basically 1. We know that pop takes only O of 1. Similarly, push also takes O of 1. Now, if there are n push and pop, we can say it will take n, right? So we use cost is equal to 1 for each pop. Okay. So then what happens here is the cost will be minimum of S or K, because we know that either I have to pop either k elements or I have to pop the entire stack contents, that is S elements. So we do not know which one we have to do beforehand. So only after knowing the current status of number of elements, we'll be able to pop. So the cost of this will be minimum of either S or K, whichever is minimum. Okay. So if K is 3 and the stack contains only 2 elements, the value of S is 2. If S is 10 and I'm asking you to pop only 3 elements where k is equal to 3, so the minimum will be k, not S. So it depends on what is the minimum value. So the worst case scenario, we can say that at any stack operation is basically O of n. So you say that for any case, if you have n push or n pop or a multi-pop which takes O of n, the worst case scenario for any single stack operation is O of n. So if you have a sequence of n operations like this, okay, then we can say that it takes around O of n square. So if you have a sequence of push, pop, and multi-pop operations, so initially the stack is empty. So we imagine that if one thing takes O of n, then for a sequence of operations, because it is happening n times again, a multi-pop itself takes O of n, and we are doing this n times. So what happens is we imagine it will be O of n square, but that is not a very tight or correct answer, you can say, because how many elements you push in that many only we can pop out. The fact that multi-pop is expensive, so basically it is because each item can be popped at most once for each item it is pushed. Only if it is pushed inside, then only you can pop it, right? So the number of pop operations cannot be more than the number of push. You cannot say less. So which is at most n. So it never goes to n square. So you can say that it is just simply O of n. So when the average cost of the operation will be O of n by n, that is the number of sequence of operations. So you can say average on the average for each operation, let it be pop, push, or multi-pop, will be only giving O of 1. So O of 1 is known as the amortized cost here. So otherwise we would have said it will cost O of n. So we are trying to take the average of each of the operation and to say that on the average, a push, a pop, and a multi-pop, even though multi-pop has repetition of pop n times, we say it will take only O of 1. Okay, because the multi-pop can work n times only if that many elements are pushed in. So you can say n elements are pushed in, then with a single multi-pop, if all the elements are pushed out, that would be maximum n. It will not go up to n square. Okay, so this is known as a aggregate method in a amortized analysis. So this is just an example showing action of a multi-pop on a stack S, which is initially in the scenario A, that 4 objects are there. So if I call multi-pop of S comma 4, you can see here, multi-pop of S comma 4, it shows the result as in B. You can see 4 elements will be deleted like this, and this will be the final status of the data structure. Now suppose next operation is multi-pop of S7, okay, which empties the stack as shown in C. But because there are fewer elements, because there are not 7 elements, we had only 2 elements. So the minimum of 7 and 2 will be taken and 2 of them will be deleted. So this is what I said before. The sequence of n operations cost at most O of n because an element can be popped, whether it is inside pop or inside multi-pop. In both the cases, only one, each time it is pushed, it can be popped. So the maximum time taken will be O of time taken for multi-pop will be O of n, and the average cost will be O of 1. Okay. Average is just averaging by the number of sequences because everything is taking maximum O of n. Okay. Okay. Next, we look at the second kind of method in amortized analysis, that is the accounting method. So what happened instead of the previous one where every operation sequence of operation was given an equal cost, it's different from here that we assign different charges to different operations. Okay, so the amount of charge that is given, charges for doing a particular work, you charge someone. So similarly here also the amount of charge that is given is known as the amortized cost. So usually amortized cost will be same or at least more than the actual cost. You can say that when the amortized cost is greater than the actual cost, like this. Okay, the difference is saved as in specific objects as credits. We call it as credit. Okay, so the credit can be used by a later operation for those operations for which the amortized cost is less than the actual cost. So it is something like this. You can say some of the operations are expensive where some are least expensive. So what we do is when the ones that are least expensive, we will charge something from them. Okay. And later, when an expensive operation comes, we try to take these charges, that is, these credits that we got from the least expensive one and give it to the more expensive one so that they don't have to bear too much. Okay. So at the sake of others, some people have to sacrifice more, even though their cost was less expensive. So we say charge something. and then we come back to the expensive operation and we reduce their cost. So we are trying to balance out the entire cost here. So as a comparison in aggregate analysis, all of the operations will have the same amortized cost. So you can say that amortized cost can differ across operations. We overcharge some of the operations early in the sequence, and this overcharge is basically known as the prepaid credit. Okay, so okay. Now this is the scenario where you can see the actual cost is denoted by the variable Ci for the ith operation in the sequence, and the amortized cost is given by Ci cap. So you can say there are many n sequence of operations. So I is the variable representing each sequence. So if you have from I is equal to 1 to n, the summation of, you can see here, the summation of I from n, amortized cost should be greater than equal to the summation of the actual cost. This should hold. So since we want to show the average cost per operation is small using amortized cost, we need to total the amortized cost. We need to show that the total amortized cost is an upper bound of the, you can see here, this should be greater than equal, we are saying, right? So the total amortized cost is an upper bound of the actual total cost. So this is an upper bound, you can see, because it is greater than equal. And this will hold for every sequence of operation. So you can say for example, if you subtract the amortized cost, sum of amortized cost minus the actual cost, which is a non-negative, then you can say that difference between these two should be greater than equal to 0 for every value of n. Okay. Now looking into, before moving on, we'll see how it can be, this accounting method can be done with the help of stack operations we learned earlier. So suppose that the actual cost of the stack operation, say push, pop, and multi-pop, right? So we can write down the cost of each one of them as push takes 1 unit, maybe you can say 1 rupee or something, and pop takes 1 unit of time or 1 rupee. This is the cost for it, okay, 1 month. And multi-pop takes minimum of whichever is minimum, you can say either S, that is the stack size of the stack, or K, either one. Now let us assign the following amortized cost. Suppose I'm giving amortized cost, a push, I'm giving amortized cost of 2. That is, I'm charging 1 rupee extra for than it what actually takes. And I'm not charging multi-pop. I'm not charging anything for the multi-pop or the pop. We are just giving it a 0. Okay. So imagine it like this. You have a stack of plates in a cafeteria, and every plate is stacked. That is, stacked means what? It is on one top of each other. It's on top of each other. And suppose that there is a 1 rupee or a $1 that represents a unit cost. When you're pushing a plate, you use $1 to pay the actual cost of the push, and we leave $1 on the plate itself as the credit. Why? Because you're charging push $2, right? Or 2 rupees. So when you're pushing a plate, you take one of the dollar for the cost of actually pushing it, and you leave one of the dollar on the plate as a credit. Now, when you're popping a plate, it should require $1, right? That $1 is already there on the plate from the push. So that, so whether it is pop or multi-pop, both are the same thing, right? Multi-pop, the difference is only that you're repeating it again and again. So it's already on the plate. $1 is extra credit on the plate. So when you're taking a plate outside, you can say that the $1 on the plate will be used to pay the actual cost of the pop or of the multi-pop. So by charging the push operation a little more, we do not charge pop or multi-pop. So that is what I said before. You at the expense of other operations. You can say the expensive operations or multi-pop operation which takes more time. the cost of that can be reduced. So this is the basic idea behind accounting method with the help of a stack operation. So when you look at the total amortized cost for n push, pop, and multi-pop, it's basically O of n. And it will be O of 1 when you take the average amortized cost for each of the operation. So the total amortized cost will be greater than equal to the total actual cost, and the amount of credit should never become negative because you will always have extra credit on the plate like said before. Okay. So this is how it looks like. A push actual cost is given there. Multi-pop also actual cost is given there. But when it comes to assigned amortized cost, we charge 2 rupees for this one, but whereas for the other one, we charge only 0 and 0. Now the second one, it is almost same, the third one, sorry, the potential method is same as the accounting method, but the something prepaid is used later. It's almost same as the accounting method. That is something prepaid. That is prepaid means what? You, on the plate, you put one extra dollar, right? So something like that. Something is prepaid and that will be used later. The concept is the same. But it is different from accounting method that the prepaid work is not stored in the form of credit, but it's in the form of potential energy. We have learned this potential energy when you go up a hill and when you go down a hill. So the potential energy, how it is gained and how you can use that energy to move up or down the hill and so on. So you can say the potential is basically associated with the data structure as a whole rather than specific objects within the data structure. You can say, I'll give you an example, you'll understand it better. What we do here is we overcharge some operations early in the sequence, just like in accounting method. And we store this overcharge in the form of not dollars or some charge like that, but instead we store it as a potential energy of the data structure. Okay, so the entire data structure state will be having a potential energy at one state. And when it moves to another state, the potential energy will change. So this is how it will be moving. So suppose that you have the initial data structure at D0. What is that? D0 means it's the first state. Say if you have a stack, first state of the stack is that it is empty, right? So after n operations, it will result in D0, D1, etc., etc., Dn operations, and each one will have a cost of, you can say, C1, C2, etc., Cn. So these are the states of the data structure and after n operations, and this will be the cost of each of the state. So what is a potential function is phi denoted by, for any state of the data structure di, potential function phi is mapped to some real number, you can say. Okay. Now the potential of d of phi is denoted by the symbol phi of d of phi. So if you're trying to find the amortized cost of I operations, we can say that the cost of any operation is simply this amortized operation with respect to this value when you're looking at this function phi is C of I cap is nothing but the actual cost plus the change in potential energy. So look at that, the actual cost, whatever is the actual cost currently for the data structure, plus the change in potential energy. What is the change in potential energy is nothing but the state of the data structure now. Okay, that is di minus 1, and the state, you can say either way. The data structure has a particular state now. In the next step, it has another state. Or you can say the data structure is currently in di state, and the previous state will be known as di minus 1, right? So the difference between the current state to the next state is known as the change in potential energy. So if it is mapping to a real number, then the value, some value will be there. Just subtract those two integers and you'll get the answer. Okay. So when you take the summation of, this is just for a single operation Ci cap. Suppose you're taking the summation for n sequence of operations, then you get it something like this: Ci plus di, phi of di minus phi of di minus 1, the whole summation you get, right? So you know that when we subtract di minus 1 for every term of I to n, this becomes a geometric series like phi of, say if it is D1, then D2 minus D1, then you will have D3 minus D2, and so on. So this state will keep on going. And finally, what happens is all the terms will cancel out because one will be a positive, one will be a negative, and so on. All the terms will cancel out except for the first term and the next term. So suppose that our first term was I starts from 1, right? So the first term will be phi of D1 minus phi of D0. Okay. Second term will be phi of D2 minus phi of D1. Third term will be phi of D3 minus phi of D2, etc., etc. till n. Okay, this will keep on going. Phi of Dn minus phi of Dn minus 1. Now what happens is D1 is one term here and D1 is another term here. So this is minus and this is plus. So we cancel these two. Then we take the second term here will be cancelled with the negative term here and so on. We keep on doing this. And finally, what will be left is the first term of the sequence and the last term of the sequence. So basically, you can say that summation of difference between terms from varying from I to n will give you a telescopic sum. A telescopic sum is something like this when you expand this, and finally you will have only these many terms left. So the summation of the actual cost plus the potential difference between the first state of the data structure and the last state, that is the end state of the data structure, that gives you the sum. So amortized cost will be calculated as cap of CI cap will be nothing but actual cost summation plus the change in potential energy of each state. So instead of doing each state, you can just take the difference between the first state and the last state. Okay. So we know that if phi of dn is greater than equal to phi of d0, by naturally because the potential energy you can say will be greater when it comes to a last state, then you can say the total amortized cost will be an upper bound of the total actual cost naturally. So the you can say that because these two values itself are greater is greater than the other one, you can say the total amortized cost will be an upper either greater or equal to the actual cost. So C cap will be greater than equal to C. But we do not know how many operations are required. So, so for every DI that is greater than this, we can say for any value of 5, we conveniently say that D0, that the first state, okay, D0 is the first state of the data structure. The potential energy of the first state will be labeled as 0, you can see here. And we can say that for any DI that is greater than, we can also say that it will be greater than the other term. So if just the first state is 0, then all the other terms naturally has to be greater than 0. Then only the difference will stay greater than 0. So if the potential change is always a positive, then I can say that the current term, you can say the current term is here. This is the current term, di minus di minus 1 should be always positive. Okay. So then the amortized cost is actually a overcharge. So you always have an increase in potential from a state to a next state, right? So the next state minus previous state will always give you a greater than 0 value. So that means you have an overcharge. Otherwise, we say it's a undercharge. So that is done so that you can pay for the actual cost, like we did for a plate, a push and pop. The same concept, the only difference is we do not talk in terms of money, we talk in terms of potential energy. Now let us solve this with the help of the stack operation. So you can see here, the potential for a stack is the number of objects in the stack. Basically, you can say some relation should be there for mapping to a real number, right? So we are going to take the potential energy of the stack as the number of objects in the stack. So initially, the state of the stack, what is the state of the stack? It is empty, right? So the potential energy of D0, if this is the current state of the stack, empty state, then you can say it is 0. And every other operation, it should be greater than equal to 0. So suppose I'm coming on to the first operation, push. Okay. Taking the first operation push, you can see the difference between potential energies di, phi di minus phi di minus 1 is nothing but, so suppose that the current state of the stack is S. Let's say I put 1 or 2 elements, something like that. So how many elements are there? S elements are there, small s. So if this is the previous state, after inserting one new element into the stack, okay, we are inserting a new element into the stack. Now, what is the state of the stack? It will be S plus 1. So look at that. So the potential change is 1 for a push. Now look at the calculate the amortized cost. Amortized cost is nothing but actual cost plus change in energy, right? Potential energy. So what is the change in potential energy? We found it as a 1. What is the cost assigned to a push operation? We already know from the previous example that it is a 1. So 1 plus 1, we have a change amortized cost of 2 per push. So same as what we learned for accounting method. Now look at the pop. Find the potential change of a pop operation. Suppose that you have three elements now. This is the state of the stack. The state of the stack is currently S. Now suppose you're deleting one element. What will be the state of the stack? It will be S minus 1. So the change in potential energy is S minus 1 minus S. That is minus 1. So what is the amortized cost? Is the actual cost plus change in energy. Actual cost is 1 and the change in energy is minus 1. So you have a amortized cost of 0. That means you are not charging anything for pop operation. Now let us come to multi-pop. Multi-pop is basically K dash, some value. We don't know which one is minimum, either S or K. Suppose that you have 5 elements in the stack, okay, and I'm asking you to pop only 3. So which is the cost involved? Only three elements are pop. So the cost involved will be 3, right? But suppose that you have only one element in the stack and I'm asking you to pop 3. So is there any need to pop 3 elements? No, we have only one element. So whichever is the minimum, either the size of the stack or the element, the number of times I'm trying to pop, that is K. So suppose that I call that as K dash because we do not know whether it is S or K. I'm temporarily calling it as K dash. So change in potential is basically the current state of the stack is S, right? But once you pop K elements, K not, it's not K, sorry, K dash. Once you pop K dash elements, it will be the state of the stack will be S minus K dash. So you get minus K dash. So the actual amortized cost is nothing but the actual cost plus the difference between both of them. So we sum it. So the actual cost is K dash, like we said before, this is K dash and the change in potential is minus K dash. So the multi-pop operation has a cost of amortized cost of 0. So you can see the amortized cost of each operation is basically uh, uh, in this case because it is charging a 2 extra, but for pop and multi-pop, even though the cost is 1, we take the cost or the potential energy from the push operation and do not charge anything for the pop or multi-pop. Okay, so you can say the amortized cost of each operation is basically O of 1 and the total amortized cost of n operations will be O of n. So again, we can say that the total amortized cost C cap of I will be an upper bound of the actual cost. Okay, so this is the basic idea. So there is one more example in the textbook with something known as binary counter. So you can have a reading of it. And if you have any doubts, you can ask. Thank you.